Discrete Mathematics Module 1, Lesson 1, Set Theory. Module 1, Lesson 1 covers the following topics: the definition of sets, describing sets, using the roster method, the set builder notation, some important sets in mathematics, empty sets and universal sets, subsets and set equality, and power sets. Discrete mathematics basically is the study of mathematical structures that are fundamentally discrete rather than continuous. Discrete mathematics, therefore, only deals with discrete objects, usually enumerated by integers. More formally, a discrete mathematics is characterized as a branch of mathematics dealing with countable sets. The sets mentioned in particular are sets of objects that may be finite or infinite. The concept and notations of discrete mathematics are actually very useful in studying and describing objects and problems in branches of computer science, such as computer algorithm, programming languages, cryptography, automated theorem proving, and software development. Conversely, computer implementations are significant in applying ideas from discrete mathematics to real-world problems, such as operations research and, in most cases, database management. As mentioned, discrete mathematics is primarily concerned with discrete objects or countable sets. A set is defined to be an unordered collection of objects. Therefore, it may be the students in this class. A set may be chairs in this room. The objects in a set are called elements or members of the set. A set is said to contain its elements. The notation often denotes that A is an element of set A, meaning A is a member of set A. If A is not a member of set A, then it's often written like this. In order to determine then elements inside your given set, we apply what you call a set builder notation. A set builder notation is a mathematical notation for describing a set by enumerating its elements or stating the properties that its members must satisfy. One of the simplest way in order to describe your given set is by a roster method, which simply lists all the elements and encloses them in braces. Given here is one such example. Note that when using this technique, ordering on the elements are not necessarily important, meaning you may write down your given elements inside your set in any given particular order. Likewise, each distinct object is either a member of your set or not. Therefore, listing it more than once does not necessarily change your given set. The ellipsis may be used to describe a set without listing all the members when the pattern is clear. One such example is the set of all letters in the English alphabet. It can be represented therefore like this. The set of all positive integers less than 100, like this, and the set of all integers less than 0, like this. Another set builder notation is to specify the property or properties that all members must satisfy. Like on this given example, Set S contains values of x which are positive integers less than 100, while on this given set, set O contains x which are odd positive integers less than 10. Or it may be described in terms of some other set that satisfies some given property. In this case, set O contains values of x which are elements of your positive integers that fall within this given particular range. Likewise, on this given set, S contains x which are real numbers that eventually satisfy this given equation. Here are some of the following sets that are often used for set builder notation, which are referred to as special sets. It may be the set of natural numbers, the set of integers, the set of positive integers, the set of rational numbers, the set of real numbers, the set of positive real numbers, or the set of complex numbers. Interval notations may also be used on your set builder notation, which may be the closed interval or the open interval, and they have varying uses such as these. The universal set U is the set containing every element under given consideration. The empty set, however, is the set whereby it contains no elements and is often symbolized like this or this. Sets can be elements also of sets, like this given particular example, this given example, and the empty set is basically different from a set containing the empty set. A Venn diagram is a systematic development that utilizes graphical illustration like geometric figures to show existing relationship among sets that are usually represented as rectangles for universal sets and circles for sets, like this. A Venn diagram may contain a universal set which includes one set or two sets or even more. Set equality. Two sets are believed equal if and only if they have the same elements. Therefore, if A and B are sets, then A or B are equal if and only if every element of set A is an element of set B. We then write them as equal sets. Note that repeated elements on your set do not matter as long as elements are exactly the same. Subsets. By definition, if set A is a subset of B, then every element of set B is likewise an element of set A, given this notation. And this eventually holds true the definition of set equality. Hence, if we're given set A to contain elements like this, and set B to contain elements like this, then therefore A is a subset of B as well as B a subset of A. Proper subsets. By definition, if A is a subset of B, however, A does not contain same elements as B, therefore it is denoted as a proper subset, whereby this corresponding definition is now true. In this particular case, the elements of your given subsets are not equivalent to the element of your given set. Hence, if every element coming from set A is an element of set B, however, A does not contain all the elements of B, then it's referred to as a proper subset. And then we have power sets. A power set is a set of all possible subsets that can be determined from your given set, which eventually includes the null set. For example, let's determine the power set of set A containing elements 0, 1, and 2. So the power set would eventually include the null or empty set, a set containing 0 only, whereby this set contains elements that are also found in set A. Therefore, it's a subset. Or a set containing 1 only, 2 only, or a set containing 0 and 1, 0 and 2, 1 and 2, or even a set containing 0, 1, and 2. So these are all subsets of your set A. Hence, if we collect them together, it is now referred to as a power set. Set cardinality implies the number of distinct elements in your set S, whereby n there is referred to be as a non-negative integer. The definition of cardinality implies the number of distinct elements, as stated on this example, that if I have a set which contains a null or empty set, basically it has 0 elements. Let S be the set of letters in the alphabet, then the cardinality of set S becomes 26. On this given particular set, I have 3 elements, noted to be 1, 2, and 3. Therefore, the cardinality of this set would be 3. And if a particular set contains a null or empty set, then that is counted as one of the set. Therefore, its cardinality would be 1. Let's evaluate a few examples. List down the elements of each of the following sets. The set of odd natural numbers less than 10. That would mean our set would contain values of 1, 3, 5, 7, and 9. Our set S this time contains values of x, which are elements of your integers that satisfy this given equation. Therefore, our set will only contain values like -1 and -2. This time, set S involves in values of natural numbers that eventually satisfy this particular equation. Therefore, our set S may contain numerous elements starting with 2, 3, 4, 5, 6, 7, 8, 9, and 10, and so on and so forth. Based on this given set now, our elements contain integers which eventually satisfy this equation. Therefore, our set S would only contain -1 and 1. And finally, this particular set contains a set of natural numbers that satisfy this given equation, whereby x is evaluated by using this formula, and k would be some natural number that would eventually satisfy this given set. So the minimum value of your element there in set S would be 5, followed by 15, followed by 29, followed by 47, followed by 69, and so on and so forth. This next example determines which of the following sets are proper subsets of other sets. So we're given set A, set B, set C, set D, and set E containing the following elements. From this particular sets, we can now say that set B is a proper subset of set A, because every element of set B is likewise seen on set A. However, set B does not contain all the elements of set A. Likewise, set C is a proper subset of set A, because every element on set C is likewise seen on set A. Set C also is a proper subset of set E, where your elements on set C are also seen on set E. Likewise, set D is a proper subset of set E, whereby elements of your set D are also found in your set E. On this next example, let's try to determine the power set of the following sets. For the power set of set A, this now involves in the null set, a set containing 2 only, a set containing 4 only, and a set containing 2 and 4. For the power set of set B this time, it contains the null set, a set containing only 3, a set containing only 5, a set containing only 6, a set containing 3 and 5, a set containing 3 and 6, a set containing 5 and 6, and finally a set containing 3, 5, and 6. As you notice, the number of subsets present on your given power set is denoted by a formula 2 raised to n, whereby n implies the number of elements found on your given set. Therefore, we expect on set C that there would be 16 subsets possible on your set C, which includes the null or empty set, a set containing only 4, a set containing only 5, a set containing only 6, a set containing only 7, a combination of 4 and 5, a set containing 4 and 6, 4 and 7, 5 and 6, 5 and 7, 6 and 7, a set containing the combination 4, 5, and 6, 4, 5, 7, 4, 6, 7, 5, 6, 7, and finally a set containing 4, 5, 6, and 7.